Okay, this is Physics 1A for Wednesday, May 12th. Today we're going to keep talking about angular momentum and look at some problems. So to summarize what we did last time, we learned about this idea of angular momentum, and I'm going to give you the kind of brief summary of how angular momentum works in three different scenarios. Whoops, I want to be on this page. I'll do this. I need to get to where I can read your Discord messages. Okay, so there's three types of angular momentum that you're going to see. There's really more, but there's three basic types that you're going to see show up in this class, okay? The first type of angular momentum is going to happen when you have an object that is a point mass, such as some mass m, that has a velocity v, let's say pointing this way, and you have some point about which you're going to define its angular momentum. Okay? If the angle made between this r vector, the position vector, and the velocity vector is phi, then we can define angular momentum, we use the symbol L for it, as being m times v times r times the sine of the angle. So this is if you have basically like a point mass, which for a lot of the problems you're going to have this. Like the first few problems we look at here, you're going to have something like this. Okay. All right. The other possibility is if you have an object that is like a rigid object that's rotating. Oh, I see what you're saying, Paige. Did everything based on a curve, but then everyone didn't do the final, so he had to remove it from this. Yeah, that makes sense. Yeah, exactly. Okay. All right. So the next possibility for defining angular momentum would be if you have like a uniform object of some type and you know its moment of inertia. So for example, let's say we take a hollow disk. Okay. So I have a hollow disk here. And let's say that it has a radius capital R and a mass m. I don't know why I said hollow disk. Let's say this is a solid disk. And let's say that it is rotating about a fixed axis that runs through the middle of it like this. So there's an axis kind of coming out of the screen. Let me draw that in a way that looks like it's coming out of the screen. So there's an axis. If there's an axis that runs through the center of this, I don't know what the best way to do this is. Let me draw an axis like that. So if there's an axis that runs through the center of this, and this object is rotating, so it's rotating like this with some angular speed omega, then what you can do is you can use the definition that I have over here for angular momentum, and you can basically sum up the individual angular momentums of the pieces of this, and what you end up finding is that the overall angular momentum of this object is going to be given by the moment of inertia of the object multiplied by the angular speed. And you can also include the vector direction of this if you want to by putting the vector symbol over L and omega. So in this case, if I have an object that's rotating around like this, it's going to have an angular momentum vector that's going to basically point this way. It points along the axis, and to figure out the direction of the angular momentum vector, you rotate your fingers in the direction of the rotation. So if you have an object that's rotating around in a circle like this, if you wrap your fingers like that, your thumb points into the page, that's the direction of the angular momentum vector. It's also the direction of the angular velocity vector. This is not always going to be important, but sometimes it will be important. Okay? Finally, there's the possibility that you can have an object that is doing both of these things at the same time. And a good example of that is like a planet as it revolves around the sun, okay? So let's say this is the sun, right here. And let's say that this is the Earth. How do I want to draw this? So here's the Earth. And let's say that we're viewing this system from overhead. So the Earth is going around in a circle like this, orbiting. And it is also spinning on its axis, right? So we're just going to say that the Earth is... Okay, what way does it rotate? It has to rotate so that okay, I'm probably going to get this wrong. I think it's going to rotate like this, though. So it has an angular speed omega, but it also has a velocity, right? Oops. A velocity vector like this. So this would be like its tangential velocity vector, right? So for this, you can have both types of angular momentum. So I'm going to name these now, okay? So this type of angular momentum we call orbital angular momentum. This one is called either spin or rotational angular momentum. I'm going to call it spin. And this one here has both, because it's rotating on its axis, but it's also orbiting around the sun, right? So we're going to need two different distances here to define what's happening here. So I'm going to, in blue here, we're going to define the distance between here and here. We're going to call that one, I don't know, let's call it big R, I guess. And let's call the radius of the Earth, we'll just call it R sub E. Okay? With this one, the total angular momentum for this object is going to be equal to the orbital angular momentum part plus the spin angular momentum. So it's going to be equal to the mass of the Earth multiplied by the velocity of the Earth, v, and then multiplied by r, plus, there's a right angle right here. So when you do sine of 90, you get 1. Plus you have the spin angular momentum term. So plus I multiplied by omega. This would be the moment of inertia of the Earth. And there we go. We could go a little bit further if we want. We could say treat the Earth as a uniform sphere. It's not a uniform sphere. It's denser in the center than it is on the outside. But if we treated it as a uniform sphere, then we would plug in 2/5 here, mass of the Earth times the radius of the Earth squared times omega. And then that would give us the total angular momentum of the combination. So you have 3 different types of angular momentum. Now, most of the problems we do, you're really just going to have these two types separate, but it is possible to have both. So I'm just pointing that out. Okay. Does anyone have any questions? Angular momentum is probably one of the more complicated topics that we've discussed in this class. And there's a really nice summary in this document here of angular momentum. It covers what I just, specifically just said here, talking about angular momentum about the center of mass, use I omega, angular momentum of a point mass with no spin. This is from the Phys 1A examples document. It's on Canvas. Same thing here. The way that we're going to use this is we're going to analyze collisions that occur that involve rotation. And this first one isn't a collision, but the next few will be. And for those, what we're going to be able to do is we're going to be able to say that when no external torque acts on the system, the total angular momentum of the system is conserved. Okay, and we call that conservation of angular momentum. So angular momentum is the third conservation law that we learned about in this class. The other two are regular momentum, conservation of energy, and now conservation of angular momentum. When you take those 3 ideas, those 3 conservation laws, and combine them with Newton's second law, you can basically describe all of classical physics. So conservation of angular momentum says that when no external torques act on a system, so that would be net torque equal to 0, then the angular momentum of the system is conserved. And the way we'll usually write that, since we're using the symbol L for angular momentum, we'll write it as the initial angular momentum is going to be equal to the final angular momentum, right? So there we go. And we can also talk about what happens when the net torque is not 0, but we'll talk about that when we get to some problems where we have to deal with that. The simplest answer is that when the net torque is not equal to 0, the net torque is going to be equal to the rate of change of the angular momentum. All right, so we're going to look at this problem right here. So different ways to define angular momentum. In general, the most general way to define angular momentum is to define it as R cross P. That will regenerate all of these definitions that we have here. Okay, so here's an example of a problem we can handle with this. So we have a small disk of mass m. It's connected to a fixed point C by a perfect chord of length L. So perfect chord means that it doesn't stretch. The small mass slides along a frictionless horizontal plane. So this whole thing is on a horizontal plane. Okay, you could think of it as like a hockey puck on an air hockey table that's connected to a string, which is connected to a fixed point. And the hockey puck is basically sliding flat on that surface. So there's no gravity here. The gravity would be pointing down into the page is what I'm trying to say, because we're on a flat surface. The small mass slides along a frictionless horizontal plane with the speed of v initial. The distance of closest approach to the fixed point is b. Determine the angular velocity omega after the chord pulls the mass into a circular path of radius L. Okay. Does this question make sense to everyone? The solution for this problem is really fast, so please ask if you have any questions now. You don't get what it means. What? Just like what it's saying, basically. So you have a flat surface. I'm going to draw my own picture of this. You have, let's say, a fixed point right here. Okay, this is like point C. And there's a string that connects this object right here to point C. And this object is sliding to the right with a velocity v. So it's going to keep sliding in a straight line, but eventually this chord right here will get tight. Let's say that happens like maybe over here. The chord gets completely tight, and then at that point, the puck is going to basically have to travel along a circular path like this. And we want to find at what angular speed it's going to travel, basically. Does that make more sense if I explain it again like that? Okay. All right, I'm going to redraw this picture using like vectors and stuff. So here's our fixed point C. Here's the mass m. It's traveling with a constant velocity to the right to begin with. So this is the velocity of the object, v. And then we have this loose chord right here. So we can consider this to be kind of like the initial position. And then eventually, what happens is that the string reaches a maximum length. And when that happens, somewhere like here maybe, like here probably. The string has a length L, as described in the problem. And at this point, the mass is going to change its direction due to the string, and its velocity vector is going to point this way. It should be at right angles. I'll try to make that angle right. Something like that. And I'm just going to call this, let's call it v prime. And the other piece of information we have is that the distance between this point and this point is b. So that distance right there is b. That's what we got. Okay, so distance of closest approach to the fixed point is b. That's this distance here. Oh, this one is called v initial in the problem, right? Okay, so let's include that. That's v initial. V initial. And if we're going to call this one v initial, we might as well call the other one v final, just to be consistent, I suppose. Okay. So what we're going to do, so this is the final position. What we're going to do is we're going to say the angular momentum in this picture, which is going to be our initial angular momentum, has to be equal to the angular momentum in the picture on the right. Okay. So what is the angular momentum here? So to determine that, what we want to do is we want to draw a vector from the coordinate c. This is going to be our fixed point that we define angular momentum about. You're welcome to choose any point you want to, but we might as well choose this point. We define this vector to be r. That's the position vector. Notice that what happens to this vector r as this mass moves to the right? Does it get shorter? Does it get longer? What happens to it? Say when the object moves from here to here, for example. What happens to that vector r? If I were to move the mass m to here, is the vector r shorter or is it longer? Gets longer. It eventually will get longer. I would say it gets shorter though, I think in this case. So this is our point C right here, right? And let's say that this represents the mass at 3 different or 4 different locations right here. If I draw this vector r right here and put it in here, it starts off like this. It's getting shorter, right? Can you all see? The vector is getting shorter. Like that one's definitely shorter. And then this one's a lot shorter. And eventually, it reaches a shortest length right here when it gets to the very top, right above point C. You can see I didn't really quite do that right. It gets, this is the point when this vector gets the shortest. But then as this mass moves to the right, that vector starts to get longer again, right? Like if the vector's here, for example, then the vector's gotten longer again, right? So would it be like moving as you move the point? Yeah. It's going to be moving basically like this. It's a mass, it's moving in a straight line, but the caveat is that it's also attached to this string right here, which means eventually that string is going to get tight, which is going to force it to move in a circle, right? But yeah, this radius vector is getting shorter, right? Okay. So as the object moves, that vector gets shorter. And our definition of how we calculate angular momentum is we need to look at this angle right here. And our angular momentum is going to be the mass of our object times the velocity of our object times the radius vector from C to where the mass m is. And then we have to multiply by the sine of the angle phi. But if we look at this expression right here, r sine phi, what's that equal to in our picture? This is a right angle, by the way. It's b, right? So b is equal to r times the sine of phi. So this basically becomes mvb. That shortest perpendicular distance, how did it say it over here? The distance of closest approach is b, right? Notice that that actually ends up giving you a value that kind of corresponds to Do you remember from torque? This distance is kind of like the lever arm, right? In torque. It's the shortest perpendicular distance to the axis. Can you all see that? That b is the shortest perpendicular distance from the velocity vector to the axis. Can everyone see that? Okay, so it's like the lever arm, right? When we were doing torque, right? Okay, does everyone agree? That's like the lever arm? Do I need to review that real quick? Are you guys with me here? Okay. Thank you for responding. Otherwise, I just keep talking. All right, so next thing to do is to come to our final position here and calculate what the angular momentum of this piece is. Maybe you all can tell me. What's the angular momentum in the final scenario going to be here? Now my object is basically rotating around in a circular path that has a radius L and it has a velocity that we call Vf. What's the angular momentum going to be here? You can use the same equation. It's basically just m times v times L, exactly. Because m times v gives us the momentum, and then you just multiply by this distance right here, because the angle between basically the L vector, or R vector, and the velocity vector is 90, so it's just mvl. I'm going to put on here sine 90. Now I need to be careful. This initial velocity on the left, that should have been v naught, so I'm putting v naught in there. This should be vf, right? So now what we can do is we can cancel out the m's, and we're solving for v final effectively. We're not really, but we'll see what we get in a second. So if we solve for v final, we get v naught times b over L is equal to v final. But the problem asks us to calculate the angular speed. We want to know at what angular speed this object is going to rotate around this circle right here. So how do I convert from the velocity, the final velocity here, which is, this is a tangential velocity. How do I convert from that into angular speed? Yeah, we take the radius of the path, which is L, and we multiply by omega, right? So if we take VF and we divide by L, that should give us omega. So from here then, omega is going to be equal to V naught B divide by L one more time, and you get L squared. That's the answer. Very simple angular momentum calculation. I want to go back to something I asked earlier. So, as I said, I asked you the question, like, what happens to this radius vector as the object m moves, right? As the object m moves to the right like this. And you all said that it got shorter. So, the next question I have is, what happens to this quantity? Or, I'll put it this way. What happens to this quantity? Let me erase this piece. This right here, mv naught r sine phi. Does that change as the object moves from here to here to here to here to here, before it gets to this, like before we get to this state when the rope is tight? As long as the rope is still slack, right? What happens to this quantity? Even really this quantity here, r sine phi. What happens to that as the object moves? Is it changing? It doesn't change. That's right, Joanne. Not changing, right? This object m could be much farther away, and the shortest perpendicular distance to the axis would never change. Sometimes if you go on to take later physics classes, this quantity b is going to be called the impact parameter, since it's the distance of closest approach. This is how they talk about it in particle collisions, when you're looking at like two protons that are getting close to each other. The distance of closest approach is called the impact parameter, because things like protons never actually touch each other. They basically they glance off of each other due to the repulsive force they feel. But yeah, this impact factor is kind of important. But the other thing I want to mention about this is, if I take a separate system that does, if I get rid of the string, right? I want to kind of emphasize why it's important that this doesn't change. If I get rid of the string, then I have a mass, and it's moving in a straight line at a constant speed. Newton's first law says that if I have an object moving in a straight line at a constant speed, it's going to keep doing that forever, basically, until it runs into something, right? So it also happens to be the case that even for an object that's traveling in a straight line, its angular momentum is constant. Because of this. Because this quantity never changes, and the velocity never changes, and the mass never changes, that means that its initial angular momentum would basically remain constant. So with no string here, this object would move in a straight line, and its angular momentum would never change about that point. Because angular momentum is conserved. It's a conserved quantity. Just like momentum is conserved. Okay. So let's look at another problem. This problem is a classic demo that you may have done in 2A. If you happen to have 2A on campus, you may have done this. I don't know. If you happen to have a nice rotating chair at your house, you can do this at home. I have a rotating chair, but it doesn't rotate very well. So I don't know if I could do this, but here we go. Okay, so this is the problem. A man is standing at the center of a frictionless turntable. Okay, so we have a turntable. So here's my turntable. This thing can rotate like this. It can rotate around in a circle. And there's a person standing on it. Okay. It says he is set rotating at 1 revolution in 2 seconds by holding a 5 kilogram block 1 meter from the axis of rotation in each hand. So this person is holding a 5 kilogram block in both hands. So he's got a 5 kilogram block here. And he has a 5 kilogram block over here. They're each the same distance away. And the whole system is rotating. I don't know, that looks like a halo. The whole system is rotating around like this. We'll draw it like this. The whole system is rotating around like this, and it says that, what does it say? 1 revolution in 2 seconds. Okay, so I'm going to write that like this. His frequency is going to be equal to 1 rev every 2 seconds, which I think we would write that as 0.5 revolutions per second. Okay, so there we go. He's holding these masses, 5 kilograms, and it says that they're 1 meter from the axis of rotation. So the axis of rotation is coming down like this, and 1 meter is going to be this distance right here. And this distance right here. Okay. Do you all know what's going to happen next? Those of you that have who here has seen this demo in 2A? If you took it a couple semesters ago or something, or maybe in high school physics or something. Have any of you seen this before? Sounds like a no. Well, if any of you have a lot of room in your home, like where you can kind of push a bunch of stuff out of the way, I would do the demo for you. It's just my chair just isn't going to rotate. Yeah, Hudson's got it. So the next thing that's going to happen is this person is going to basically take the 2 5 kilogram objects and he's going to pull them into his body, and the result is going to be that he's going to move faster, basically. A lot faster, actually. So that's kind of the demo. You can do this at home. All you need is a chair, and ideally you need some weights, okay? Any size of weight will work. A 10-pound weight will work. It doesn't have to be that big. An 8-pound weight would work too. It's exactly like spinning on ice, Johan, that's right. This is what we're about to describe right here is kind of the principle behind the way figure skating works, at least the rotations in figure skating, okay? And we'll talk about figure skating and high dive, diving, rotations in diving after we're done with this. But okay, so this is our initial position right here. And then what happens, it says, he then drops his arms so that each mass is 20 centimeters from the axis of rotation. So we'll draw this again, and we'll just move his arms in. So we've got our turntable down here. And we got our person standing on it. And now the difference is that he's basically going to pull his arms in. So I'll draw it like this. We'll just say he's kind of holding the mast like this. And like this. The same masses. I'm drawing them a little smaller here. I probably shouldn't, but... So the same masses, the 5 kilogram mass and the 5 kilogram mass. But now they're 20 centimeters from the axis of rotation. So he's pulled them in about 80% closer. So now, where to draw this? Okay, so the distance from here to here now is 20 cm in both cases. So that's going to be just basically this distance right here. That distance is 20 cm now. Otherwise, everything else stays the same. The other piece of information that we have, as a result now, the person is going to be moving with an even larger angular speed that we're going to call omega final, and we're trying to calculate this eventually. Okay, the other piece of information that we know is that the moment of inertia I of the man plus the table is 6 kilogram meters squared, and this doesn't change, okay? So we'll just write down here that the moment of inertia of man plus table is equal to 6 kilogram meter squared, okay? And again, the idea here is that if you hold these masses out, you get yourself rotating. You need to be rotating. You almost need another person to do this. You don't really need another person, but it helps. Get them to get you rotating as fast as you can, and then pull your hands in. I can maybe try to do it with this chair. I'm almost certain it's not going to work. Anyway, but if you have a nice rotating chair at your home, then it will work really well. You need to keep your legs in and stuff too. Okay, moment of inertia of man plus table is 6 kilogram meter squared. The first question is, part A, find the initial and final rotational inertia. Okay, so part A. We want to find the initial moment of inertia. I'll call it I naught. So I would say that to find the initial moment of inertia, well, maybe you all can tell me, what do I need to do? We're given the moment of inertia of the man plus table. We're not given the moment of inertia of these 5 kilogram blocks right here. So what do I need to do to figure out the total moment of inertia of my system here? We need to know the moment of inertia of the blocks, right? Pretty much. So what I'm going to do is I'm going to say that the moment of inertia of... I'm just going to put man plus table plus the moment of inertia of the blocks. That should give us our initial moment of inertia. Okay. All right, so initial moment of inertia. It's not energy that's being transferred, Andrew. It's angular momentum. Okay, so the initial moment of inertia is going to be equal to I of man plus table. We're given that that's 6. And if I want to figure out the moment of inertia for the blocks, what should I do for these? I'm going to say you can treat them as point masses. So treat the block as if it's just a point that's rotating around like this at a distance of 1 meter away. What's the moment of inertia for an object like that if I can treat this as a point mass? It's just mr squared exactly. So this is going to be equal to the mass of the block, which is 5 kilograms, times the distance from the center, which is 1 meter, squared. Okay, so for these, basically, the moment of inertia of this object is going to be basically mr squared. And this moment of inertia over here is going to be mr squared for this one. For these two, each one of this is going to be mr squared. So we have 2 of them, so we need to multiply by 2. And that's going to give us an answer of, looks like 16 maybe? Okay. Does everyone understand? Does anyone have any questions? Yes, that's right, Bjohan. Okay, and then doing the same calculation for the final scenario, moment of inertia of man plus table is 6. Moment of inertia of the blocks is going to be, again, 2 times their mass. And now we multiply by the 20 centimeter distance, so by 0.2 meters whole squared. And this one then, so let's see, 10 times 0.04 is 0.4, so I think your answer here is going to be like 6.4. Do you all agree? Okay. By how much has the moment of inertia of the system decreased? By what factor has it decreased? Is that what it is? It's 2.5? 16 divided by 6.4 is 2.5? That sounds about right. Okay, so probably what we'll figure out then is that the final angular speed of this system is going to be 2.5 times faster. That's probably what's going to happen. Okay, part B. Find the final angular velocity. Let's use a different color. Okay, the equation we want to use for this is our conservation of angular momentum, initial angular momentum equal to final angular momentum. Because I have a system that is doing pure rotation and it's not like orbiting, the previous problem was an orbital angular momentum problem. This is a rotational angular momentum problem, or spin angular momentum. Then this is going to have initial moment of inertia equal to I initial times omega initial. That's the other version of the other version of angular momentum that we discussed. And the final angular momentum is going to be I final omega final. We already know what I initial is, and we already know what I final is. But with omega, one thing we can do real quick over here is to say that there's a relationship omega to frequency, which is omega is equal to 2 pi times frequency. So we have two options here. I can either replace each of my omegas here for frequency, since we already have this one in frequency. I think that's what we'll probably do. Or I can convert this frequency into angular speed, right? Doesn't really matter. You'll get the same answer either way. So I'm just going to leave it in frequency. So we're going to say I initial times 2 pi f initial, we're going to call this the initial angular frequency right here, is equal to I final times 2 pi final frequency, f final, which is going to be the frequency in this case, f final. And yeah, the 2 pi's cancel. So we end up getting that the final frequency is equal to I initial divided by I final multiplied by omega initial. And since you said that this ratio ends up being 2.5, whoops, I made a mistake here, then our final frequency should be 2.5 times as fast. Should have been f initial. So on the right-hand side, we have I initial, which is 16, divided by I final, which is 6.4. I'm going to not put units on there because this is a ratio, which means the units cancel. We multiply by the initial frequency, which is 0.5 revolutions per second. And I think that we're going to get, what are we going to get? You all tell me. 1.25. The problem asks us to calculate the final angular frequency, though, so we need to multiply that by 2 pi. So what do you get if you multiply this by 2 pi? Oh, 1.25. Yeah, 7.85 is what you all got, right? Okay, good. Okay, so 7.85. So that is our answer for part B. It's a lot faster, right? 2.5 times as fast is a lot. Just to give some kind of perspective on this, suppose you're driving down the highway at, I don't know, 50 miles an hour. If your speed were to increase by a factor of 2.5, how fast would you be going? 250? Is that right? That can't be right. Be 125, I think. Yeah, suppose you're driving down the freeway at 50 miles an hour and you increase your speed by 2.5. Yeah, you'd be going 125 miles an hour. That's a lot faster, right? It's a lot faster. 125 is really fast. But the crazy thing about this particular situation is if you actually do this, which is too bad, we have the ability to show you this like at the school, you feel like you're going insanely fast. It's crazy. It's really crazy how fast, just by taking your arms and moving them in, you speed up almost immediately. As you bring your arms in, you go faster and faster and faster and faster and faster. And then if you want to slow down, you can just pull your arms back out, making yourself bigger, which means you have a bigger moment of inertia, which will slow you down. This would work in space too. If you were, flying away from a spaceship and you were spinning out of control, if you make your body really big, it'll slow down your spin rate. Okay. Does anyone have any questions about parts A and B? Okay, part C says to find the change in kinetic energy and its cause, if any. So if we want to find the change in kinetic energy, we just want to basically take the final kinetic energy of our system minus the initial kinetic energy of our system. And in this case, that's going to be 1/2 the final moment of inertia times omega final squared minus 1/2 I initial omega initial squared. Do you think the kinetic energy is going to increase or decrease in this case? What do you all think? Or is it going to be the same? Do you think the kinetic energy is going to increase, decrease, stay the same? What do you think? Just put an answer in the chat. Doesn't matter if you get it right or wrong. I just want you to kind of think about it and just write what you think. Just make a guess. Okay, a few different people said increase, one person said decrease. All right, let's see what happens. Gives more people a chance to answer. I think it's always a good idea to kind of like think about what you expect an answer to be before you do it. Oh, whoops. This is a mistake down here. Sorry about this. I'll put it in a different color when I fix it. This should have been 7.585 radians per second. Sorry about that. That should have been radians per second. Okay, omega final squared is 7.85. Minus, I'm going to put this down the second line here because we're kind of running out of room. 1/2 I initial was 16. And omega initial, we did never actually calculate that, so I'm just going to put 2 pi times 0.5 rev per second. That'll convert that over into angular speed. We're squaring that. So this is going to be equal to the change in kinetic energy, and I still have room to write down here. The change in kinetic energy then is going to be equal to, go over to calculator here. Okay, what do you all get for this answer? That's what I got, 118. Do you all agree? Give you a second. Yeah? What'd I say? 118? Joules. Okay, so it's positive, and we did final minus initial, so the kinetic energy increased. And we had no reason to think that kinetic energy would stay the same. Well, maybe we could start there. Why did it change? And where did the change come from? There's a couple different ways that kinetic energy can change, right? One simple way that kinetic energy of an object can change would be if I take an object that's sitting at rest and I drop it, its kinetic energy goes up. But that's because gravity does work on it, right? In general, when kinetic energy of a system changes, there has to be work done somewhere, or some kind of energy conversion process. Those are the only two possibilities. So what do y'all think? What's the cause of the increase in kinetic energy in this case? The angular velocity increased, that's right. And because the angular velocity increased, as a result, the kinetic energy changed, that's right. But what allowed that to happen? Like, I guess what I'm asking is, our idea of conservation of energy states basically that energy is a conserved quantity. You can change its form, like from mechanical energy into thermal energy, like heat, or you can turn chemical energy, like in a firecracker, into kinetic energy when it explodes. We personally can turn our chemical energy when we eat food, we get chemical energy in the form of calories, right? Calories are just another measurement of energy. We eat food, we use that to provide energy for us to perform work. Basically, we convert the food into motion, which means mechanical energy, right? So what's the cause in this case? What form of energy was converted into kinetic energy in this case? And if you could describe it anyway, what caused that to happen? Any ideas? I can give you another hint. This is the question. Find the change in kinetic energy and its cause, if any. That's the question. Would it be the moment of inertia? The person is definitely spinning faster because the moment of inertia changed, yes. I don't know if that's exactly the answer, but it's maybe related to that, yeah. Mm-hmm. Yeah, what about that, Andrew? The moment the person reduces the radius to the axis of rotation. Did the person need to do any work to do this? Did the person have to expend any energy to do this? Yeah, okay, I guess maybe this question's a little bit tricky. I'm kind of saying all the things that normally would lead people to answer. This isn't. He doesn't just move his arms in for free, right? Take two weights and hold them. It's not easy to just hold weights there, right? And then take those weights and bring them into your body. That takes work, right? That takes work, flat out. It just takes work. An inanimate object can't do this, right? If I make a a dummy or something, and I put them on a turntable, and I give them weights in their hands, and I, and I spin it. A person, unless you have a person here to actively do some motion, then yeah, there's no way that you're going to get this increase in energy. But it comes from the fact that this person has to expend energy to move these in, basically. That takes work. And that's where the increase in kinetic energy comes from. Okay, this is definitely a really good problem. It's always made better by actually doing a demo, but one thing we can say now that we have an understanding of what's happening here, I mean some understanding of what's happening here, is, yeah, like this is basically what happens when an ice skater tries to do like a triple axel. I don't know if you all watch ice skating, I don't know. But it used to be a lot easier to watch the Olympics than it is these days. It used to be kind of available for everyone, and I think it kind of is nowadays too, but with a figure skater, what happens is, I'll do my best to kind of draw a picture of this. They're skating along, right? So you've got your figure skater, here's the skates. And let's say that they want to jump and they want to spin, okay, right? So what you do is, they put their arms out as far as they can before they jump. They start a jump and rotate at the same time, right? So they jump off the ice, but at the same time they start to rotate, basically. And then when they're in the air up here, they basically keep their legs as close to the center of their body as they can, and they keep their arms as close to the center of their body as they can. And what happens is that whatever rotation rate they had as they jumped, once they get into the air and they're able to spin really fast, they bring their arms in like this. And so what happens is, in this position, they have a big moment of inertia. And then when they bring their arms in like this, their moment of inertia gets really small. And as a result, what happens is that if they have a small angular frequency right here, then they get a big angular frequency right here. So if they're rotating at some small rate here, they're now rotating really fast, right? And this is how skaters can jump in the air and do like 3 complete twists, which is, I think, what's called a triple axel, before they land, right? But this isn't really the whole story, because if you got spinning really, really fast, right, and then you just landed on the ice, chances are that the moment that your skate hits the ice and like sticks in the ice, it's going to torque around your ankle and you're just going to fall over, right? Which is what happens sometimes to figure skaters. I mean, no one's perfect. Sometimes you just make mistakes, and it takes a lot of practice to get good at this stuff, right? So ideally what you want to do is you want to stop rotating before you hit the ground, right? And hopefully the answer to this should be easy for you. What does the person need to do to slow down the rotation before they hit the ground, so that they can like land nicely, basically? Yeah, they just need to push their arms out again, right? That'll slow down the rotation rate, which will make it easier for them to hit the ice and not fall over, basically, right? That's it. That's conservation of angular momentum, and how it kind of explains what's happening in really any type. You can kind of, I don't know if any of you watch sports at all. Maybe some of you just never watch sports, but anytime you're watching, so where does this show up? This shows up in figure skating. It shows up in like BMX, a lot of the X Games stuff. So like almost all the skateboarding stuff. Anytime you see someone, Andrew said skateboarding, right? If you go watch people do like large number of spins in skateboarding, like go watch someone do a 900, you'll notice they do exactly this. They do exactly this kind of stuff. They start off, they jump into, they launch off of the half pipe or whatever, and they bring their body really, really small. They do a bunch of rotations, and then they make their body slightly large again when they hit the ramp. It's not nearly as obvious as it is with some other sports, though, because like diving is another one where it's really obvious. Because with diving, what happens is that you have, you've got a pool, and you have, like, let's say, a 10-meter platform, for example. So you've got a person that jumps off up here. And it's really the same concept, except now they're going to flip instead of twist, right? They start, you will see this every single time if you watch someone dive at these events. They start with their arms completely above their head before they jump, right? Or sometimes they start doing a handstand, right? There's basically 2 different ways that they start these jumps off these 10-meter platforms. They either start with their hands completely extended, or they start by doing a handstand, which is basically the same thing upside down. And then if they're standing straight up, they either fall off or they jump off, and they force themselves to start rotating. And then once they're in the air, they just basically curl up into a ball, right? They bring their hands and their knees as close into their body as they possibly can. and that causes them to rotate around really fast. So they do a bunch of flips, right? Maybe like 3.5, 4 flips or something like that. But then once they get to the pool, they got to slow down again. So they extend their body so that they're straight, and that allows them to enter the pool, and not make any splash. So it's the exact same concept. It's just conservation of angular momentum. If the person never curled their arms and their legs together like this, they wouldn't be able to do nearly as many flips, right? Because each flip is a revolution. They only have a certain amount of time before they're going to hit the ground, something like, I think it's like 2 seconds maybe less. So the number of flips they can do is dependent on how fast they can rotate. And the only way to rotate really fast is to just make their body really small while they're in the air. Because you can change rotation while you're in the air. Okay, anyone have any questions? Rotational motion is very different from linear motion. When you jump off of a diving board and you start falling to the ground, you really can't stop yourself from falling, right? There's no way after you jump off of this, you're going to hit the water. There's nothing you can do about that, right? The only thing you can control is how fast you rotate while you're doing it. So rotational motion is very different because you can actually alter your own rotational motion, whereas you really often cannot alter your own linear motion once you're in free fall, right? Once you're in free fall, you're just going to keep falling. You can't control that. You can't jump off of the air, right? But you can change your rotational motion through the idea of conservation of angular momentum. Okay, any questions? Do we have time before we go on to F1 and to do this other problem? I'd really like to do this other problem because it'll help you to get set up to do some things. So we're going to do it. So we're going to do this problem, and then we're going to take a break, and when we come back, we're going to talk about F1. Okay. So this problem is a little different, and it's going to require that we review this real quick. So we just did 2 angular momentum problems, but in both cases, there was really only one object. In the case of the ball and the string, it was just the ball. In the case of the person with the masses in their hands and the turntable, all 3 of those things were basically one object, right? The person never dropped the masses, for example. Everything was just one object here, right? And we were able to calculate the moment of inertia of just that one thing. So the next possibility are collisions, okay? And when you have a 2-body interaction, which is a collision, for me, this is the most important part of this document. It shows up on the second page. So this is the angular momentum. It's from the Physics 1A examples pack. It's on Canvas. This portion right here is the most important. You really need these pieces of information here to fully understand what's happening in these problems. So I'm going to copy paste it in here. We'll put this down here, and this will be in the notes. But what does this say? 2-body interactions, collisions. No friction and no pivot point. Okay. In this case, when there is no fixed pivot point, okay, we're going to use conservation of linear momentum, and we're also going to use conservation of angular momentum. And when there's no pivot, we're going to choose the center of mass of the system for an axis. When there is a pivot point, it says a bunch of stuff here, but the only thing we're going to use is conservation of angular momentum, okay? So to summarize what this says is when you have no friction and no pivot, which is the first problem that we're going to do here, okay? For this one, you get both conservation of linear momentum and angular momentum. You're going to use both of these equations in these problems, okay? And this is the other piece that's important. We're going to choose the center of mass of the system for our axis. That's what we're going to do in the problem we're going to do. Problems we're going to do on Monday are going to be these type of problems. We're going to do both, but we're also going to look at these type of problems when you do have a pivot point. When you have a pivot point, the only thing you can use is conservation of angular momentum about the pivot, okay? So I'm just going to give you an example of problem type B. The problem type Bs are going to look like this. You're going to have a fixed axis. You're going to have something like a door or a swinging something. Think like a doggy door that can swing kind of like this, basically, about some fixed axis of rotation like this. And the idea is going to be, suppose that I take a lump of clay and I throw it at the door and it sticks on the door. The question is going to be, what's the angular speed of the door plus the clay after the collision, okay? This is with a pivot point, so we're only going to be able to use conservation of angular momentum to solve this problem, okay? And we'll see an example of A when we do example 4 here, okay? So keep this in mind when you're doing your angular momentum problems. I would say the vast majority of problems on that homework assignment are going to be like this. I know problems like this show up on your lab manual too. So read this, or at least try to internalize what I just said, okay? All right, we'll return to that as we're doing this problem. So here's the problem. Two small masses, m and 2m, here and here, are joined by a light, and by light we're going to mean massless, rigid rod of length L, right there, and lay on a horizontal frictionless plane. A disk of mass m is sliding at a speed v initial towards the smaller mass right here at the top. It hits and sticks to the smaller mass, and we want to do all these things right here, okay? So I want to repeat what's happening in the problem. So there's a horizontal frictionless plane, so you can think about this like an air hockey table or something like that, and you've got like 4 pucks. These 2 pucks, m and 2m, are connected by a rod. That means that they can't separate from each other, okay? They can't separate from each other. These are stuck together. And the mass little m comes along and hits them, okay? Now, I don't have like a good demo of like what this looks like, but the idea would be like if you have, I don't know how much of this, you can't even see black on this really, can you? The idea would be I have this pen right here sitting on this table. The idea would be like something, I'm going to have a hard time getting this to stay still. Something comes along and hits one edge of it and then sticks to it, and then the whole system starts to rotate. It's probably easier to hold if I do like this. Like something comes along here, sticks to the end of this, and then the whole system starts to rotate. Okay, any questions about the setup for this problem? About what's going on? Okay. Part A. This says to find the center of mass of this combination and its final linear velocity. Okay, so once these objects stick together, it's going to look something like this. So we're going to have copy, paste, initial, final. So here's our initial. The initial is going to involve I didn't want to do that. I just want to put a dot here. Okay. So now the initial situation is you have mass m here, you have mass 2m on this side, and we have mass little m moving to the right with an initial velocity v initial. The final situation is going to be these two stick together. So we now have basically 2m up here and 2m down here. And now what's going to happen is the system is going to rotate with some angular speed. We don't know what it is. We'll call it omega final. But in addition, because this mass plus 2 mass plus the rod that's connecting to them, because they are not fixed in place, what's also going to happen is that the center of mass of the system is going to move to the right like this. And that is one of the things we want to calculate. The velocity of the center of mass. So this is going to be the center of mass. This part of the problem is really easy. So let's find the center of mass. Well, if I have 2m over here and 2m over here, would you all agree the center of mass is going to be right in between them? That makes sense, right? Okay. Do you all want me to do the calculation? I'll just do it real fast. If you want to find center of mass, what you need to do is you need to pick a point. I'll pick this point right here. We'll call it y equal to 0, right? And then the y-coordinate of the center of mass is going to be equal to then. You take each of your masses, so we have this mass 2m, and you multiply by the distance to that, and since this is L right here, then the distance to the mass 2m on top is L, plus, I'm picking this point to be y equal to 0, so I'm kind of just starting from this point. You add to that 2m times the distance from this point, which is 0, and you divide by the total mass, which is 4m, and you get an answer of L over 2. That's the location of the center of mass right there in the middle. Okay. All right. So let's get rid of that. I'm going to relay you that information now. So L over 2, and that would be in reference to this point, so that means it's right there in the middle. Okay. Let's go ahead and go through and calculate this. These kinds of problems, in my opinion, they are a little bit daunting. They're a little bit challenging when you first look at them. But as you will see when we go through the calculation here, the solutions are pretty simple. Okay, part A said to find the center of mass, we did that, and its final linear velocity. Okay, so how are we going to do that? How are we going to find the velocity of the center of mass right here? Well, because this is a situation where we have, let's go back here a little bit, no friction in the problem, horizontal frictionless plane, and we have no pivot point. There's no rigid pivot point. That is to say, there's no like fixed rigid pivot point here about which the system would rotate. If there was, then this mass would hit the top mass and they would just rotate around in a circle around a fixed pivot. But there is no pivot. And that's why this whole thing, when they combine together, is going to be rotating and it's going to be sliding to the right. But it's going to be doing both things. It's going to be rotating around in a circle about the center of mass, and it's going to be sliding to the right. So, to figure this out, it says we can use both conservation of linear momentum and conservation of angular momentum. And we're going to choose the center of mass for our axis. So let's use conservation of linear momentum then to find this velocity. It is, after all, a linear velocity, right? So we'll say the initial momentum of my system should be equal to the final momentum of my system. And this would break down into x and y directions, but everything in this problem is traveling in the x direction. So what's the initial momentum in my system in either this picture or this picture? These are both the same picture. What's the initial momentum of my system? mv naught. Yep, the mass of this block, or this whatever, times the initial velocity v naught. And what's the final momentum? So this is a little bit different, but whenever I have a mass 2m here, a mass 2m here, and they're connected together, if I want to find the momentum, I just need the total mass of my system multiplied by the velocity of the center of mass. So the total mass of my system is 4m, right? And we multiply that by velocity of the center of mass, which is what we're trying to solve for. Okay, so the m's cancel out, and we get that if we take v initial and we divide by 4, that gives us the velocity of the center of mass. And hopefully this makes a little bit of sense. The idea is that the system is 4 times as big as it was to begin with, right? We had one mass with a velocity v initial. Now we have 4 masses, and they have to basically split all of that initial speed. So that's why it's divided by 4. Okay. Part B says, find the final rotational inertia about this center of mass and the final angular velocity about this center of mass. So final rotational inertia is the moment of inertia. And I final, in this case, I would say is going to be equal to. So we need to know the moment of inertia about the center of the object, right? And we've got 2 up here. And it is a distance from the center of L over 2 away. So we would basically be using, for each mass, the moment of inertia for a point mass, as we said before, is basically m times r squared, right? Where r is the distance to the axis. So in this case, we have 2m multiplied by L over 2 whole squared, plus another 2m on the bottom that is also L over 2 away. And, oh, I left off the m here. Okay. What's this going to give us? So 1 over 4 times 2 is a half. 1 over 4 times 2 is a half. I think we just end up getting ml squared, right? Yeah? Okay. Next it says to find the angular velocity about this center of mass. Okay, for that, what we're going to do is we're going to use conservation of angular momentum because it involves angular frequency. So we need the initial angular momentum and the final angular momentum. For the final angular momentum, we're going to have I final times omega final. And for the initial angular momentum, what's that going to be? Zero? Okay, I'm glad you answered that. Christy, are you saying it's zero because this object is not rotating? Is that why you're saying it's zero? And this piece right here is not rotating? Yeah, okay. I'm glad you said that. Because that's how I thought about this stuff whenever I was first learning it too, and it's not correct, but it is something that people commonly think. So let's dispel that belief. You can have angular momentum even when an object moves in a straight line. Let's go back and see where that has come up before. Right here. I have a mass m moving to the right with some constant velocity v. I have some fixed point right here. I can define the angular momentum. Come down to the second problem here. In this problem, we just had a mass moving at a constant velocity. And we could still define angular momentum, because angular momentum is just mvr sine theta, or sine phi, or whatever. Okay, so even when an object moves in a straight line, it can still have angular momentum. The only thing you need is you need an axis about which to define it, right? So let's go back to our two-body interaction collision thing right here. With no pivot, that's what we have is no pivot, we use the center of mass of the system for an axis. And this is going to be before and after the collision, okay? Before and after the collision. So that's almost right, Tombui. You want to try again? Remember, we're going to use the center of mass of the system as an axis. And I don't mean the center of mass of m plus 2m. I mean the center of mass after the collision. So Joanne's got it right. So this is the center of mass, or what it's going to be after the collision, basically, right? So instead of calling it the center of mass, I'm just going to call it the axis. So since this is L over 2, my initial is going to be m v initial times L over 2. This is kind of confusing. And we're going to do harder problems, too. So if you don't understand what I just did, now would be a really good time to ask. Because pretty soon we're going to look at problems where the center of mass is not right in the middle, and it gets even trickier. I think the simplest way to understand the equation on the left here is just imagine what the system looks like right before the mass gets to here. And it has that velocity v initial. Because then the perpendicular distance is just L over 2. So it's m v naught times L over 2. But an important piece of this is the fact that if I were to draw a radius vector like this and put an angle phi in here, what we saw in the first problem we did was that r sine phi was a constant. In this case, it's L over 2. In the first problem we did, it was b, right? Yeah. This quantity b is constant. The distance of closest approach is going to be constant. So that's why we use that in this case too. So that's our expression, and we're going to do some math now. Are there any other questions? Okay, let's finish this up. So mv naught L over 2, we're doing on that side. I final, we found right here that the final moment of inertia after the collision occurs ends up being m times L squared. Omega final is what we're solving for. So solving this for omega final, we're going to get omega final, the masses cancel, is v naught divided by 2L, I believe. Is that like right? Mass, L. What time is it? We started at like 18 after. We are really long. I'll leave the last two for you to do yourself. Part D is just not very interesting, but you can find for yourself if mechanical energy is conserved. I don't think mechanical energy is conserved in this case. In fact, I don't think it possibly can be, because it's an inelastic collision, perfectly inelastic for that matter. And if you remember the problems we did in the momentum chapter, when you have inelastic collisions, the energy